So back in 2009, Rich Hickey gave a talk, Are We There Yet?, which was a talk on time in object-oriented languages. But this isn't time like with clocks or dates, but it's on the nature of process and change. I watched this talk as part of my journey on learning the motivations of Clojure, the programming language. Like many of his talks, though, his ideas have many applications outside of Clojure. So I, only later, after grad school and industry experience, did I get to appreciate all the nuggets in his talk. So Rich basically says, we are entrenched in habit. We don't step back and reformulate the problem. So a recurring theme in my experience is how we get used to our pain points. It's like how we acclimate to a bad smell in the room. Like only after we've left the room and then come back do we realize like, oh wow, this smells pretty bad. So when it comes to development, for example, we get used to long build times and we just go and make a sandwich. We stop thinking about whether this trouble is even acceptable. What's worse is that we can fall into these bad habits unconsciously and over time. Consider how at work you might be constrained to just a few programming languages, and the features of these programming languages, whether they're good or bad, are always going to be grouped together. So thus, naturally and unknowingly, we will potentially adopt some bad practices. To make matters worse, success in the industry breeds this type of conservatism that reinforces this recurrence of these grouped patterns. So we don't truly believe that things are perfect, and we can pose that object-oriented programming can have both good and bad aspects. And we might be blind or numb to these aspects. So the question then is, how can we identify its faults? We need to have times of reflection in order to make progress on things of habit. So in practice, this doesn't come up as often as we would hope. And when it does come up, it's usually when we're looking at some sort of comparison. And that makes sense because of this comparison cognitive bias. So only when the situation presents itself as having a clear alternative that we then realize the downside of the current tool. Then when we can compare tool A to tool B, we find it's now easier to see its flaws. So that does kind of bring up a good question, which is like, how can we identify flaws without having something to compare it to? But we can think about that later. So typically a software engineer will switch to a different tool when it has some sort of impact on their productivity. But what underlies this impact on productivity? The key underlying factor is incidental complexity, which is not complexity of the problem domain, but complexity that comes from using the tool, feature, or component. Software engineers manage complexity. In the industry, in my experience, we see that complexity is increasing over time. There are now concurrent agents, there's more data, we require more flexibility, so the expectations are only increasing. And as always, we have a limited amount of time in the day to work on problems. Some examples are like a live data processing framework that has to make decisions and take actions. Consider something more specific like AWS's Elastic Container Service, which has to maintain some instance count over time. Just think of all the challenges of the different interacting systems and the scale requirements. So it's the job of the engineer to contain the complexity so that it's solvable within the time constraints and the resourcing constraints. So it's useful to ask, are the problems we're solving part of the problem domain or a problem we just put in front of ourselves because of the tool that we chose? And we know that we can more easily see the presence of incidental complexity by noting the difference in cost between the tools. Incidental complexity manifests in the cost of choosing a tool to solve a problem versus some alternative. Incidental complexity comes from the ideas behind our tools, the way they work, the way they don't work, and the resulting workarounds, because we still have to solve the problems at the end of the day. It's important to ask ourselves, what problems did you give yourself by choosing a tool language development strategy? So in recap, we become numb to common painful patterns. We will unknowingly adopt bad practices or tools. Sometimes we switch tools when we learn of alternatives. We switch due to differences in incidental complexity, the cost of using a tool, not from the challenges of the problem domain. We should strive to be more aware of the cost of choosing a tool. What do we get by choosing a particular object-oriented language? Rich Hickey claims that there's a common shared features, Smalltalk, Java, C#, Python, such as single dispatch over type, interfaces, classes, inheritance, fields, methods, garbage collection. Some differences are mixins versus interfaces, static versus dynamic typing. There's some interesting discussion here. Semicolons versus indentations versus blocks, closures versus inner classes. Rich Hickey claims that these differences are small. After all, learning Java, Python, Ruby, it's all pretty easy. Different cars, same road. So what has had an impact? Well, we know going from assembly languages to C has helped because we went from having no types to some type of type validation. Going from manual memory management to garbage collection also helps because of this reduction in complexity. So when would you choose a more primitive choice? When the problem is directly related to the manual control, like when you need to manage the memory, the bits, or operators directly. What about when you're moving between sets of languages, like Java, Python, Smalltalk, C#? Instead, Rich Hickey suggests we ask, are we driving down the wrong road? So ultimately, Rich Hickey wants to just focus on fundamental or foundational problems because those have more impact if they're solved. So something particularly bad that he talks about is hidden complexity, and something that's particularly nasty is hidden incidental complexity. The reason is we know to avoid it or respect it when it's obvious, but when it's hidden, then it's going to continue to hurt us over time. Or even worse, when the stakes are higher, it'll bite us then, and it'll incur a much larger cost. So Rich Hickey brings up this important person, Alfred North Whitehead, who's a mathematician and philosopher. And he's been referring to him in his talk by presenting a lot of his quotes. So one of his important quotes is, "Seek simplicity, distrust it," which is that we should seek simplicity, but be wary of claims of simplicity. Let's look at some actual examples. So imagine we have a function bar that returns a pointer to type foo, and we're storing this pointer into baz. This is simple operations, right? Where you just have new, delete, pass, dereference. But there's some hidden complexity. Do you have to delete the pointer? Can you save it? Can you hand it to someone? So some improvements. So I noticed that Zig, the language, retains this complexity but removes the veil that hides it. So it's worth checking out how they do that. Rust has semantics for ownership, such as borrowing, etc. Newer C++ have these shared unique pointers but still have to decide among them. Garbage collection, which is automatic memory management, removes a huge amount of this incidental complexity. So in manual memory management, the programmer keeps tracks of who owns what. What owns what is implicit in the code, and only known by the programmer or as part of convention. There is some work in this area, like with Rust, but where it is explicit who the owner is. Rich Hickey believes that the lack of garbage collection is what prevented C++ from being a good library language, given that Java had a much larger reusable set of libraries compared to C++. One important question we should always be thinking about when programming is, what problems are trivial to you? Maybe we can make an easy trade-off. Can we throw more RAM at it and use automatic memory management? Do we already have enough RAM for this? Sometimes there are easy wins. So complexity analysis 2. Java. So Java has a tracing garbage collector. It's simple and only has references to dynamic memory, right? So some hidden complexity. It's the same syntax for references to mutable and immutable. Can you see a consistent value? Is consistency maintained when the ordering of future callers is unknown? What happens in the face of concurrency when there is a possibility of simultaneous access? Can we remember this value? Is this value stable? If references are aliased or mutated, who is affected? There is no automatic time management, so this complexity persists. Why did java.util.date switch to immutable? They wanted to avoid the chaos of people changing dates while they were being used. So in recap, we should focus on significant differences. Object-oriented languages are very similar. Be wary of hidden incidental complexity. You pay for these costs many times over. So a big insight here is there's a demand for direct tooling for time management. Hickey makes an interesting point about perceived complexity. Simplicity is often assumed from familiarity. Programmers might feel that since the surface syntax is familiar, the programming language is simple. From Hickey's Simple Made Easy, we know that simplicity is not about being familiar, but instead about taking things apart. Familiarity induces blindness. So reiterating from the beginning of this talk, we acclimate to complexity, and then it becomes hidden complexity. And then this complexity slows progress, since we can no longer understand the large program. How do we know we can't understand? Because we have to run big test suites every single time we make a change. This is because we assume a very type of coupling, where we can't determine the scope of the effects of the changes to our programs. Adding concurrency, again, is only going to make this worse. Hickey predicted that concurrency will cause a major shift in language design. But in my experience, concurrency capabilities of languages remain largely untapped. Most code is still just single-threaded. Only a few specialized libraries utilize parallelism. We've simply avoided concurrency as much as possible. Civilization advances by increasing the number of important operations we can perform without thinking about them. We don't first reach for assembly language anymore. We can dive to it as needed, but we don't normally operate at that level. Instead, we usually strive to code at a higher level of abstraction. If you look at how fourth programming languages are constructed, they always first build up their abstractions and then express the final program with all the built-up components. We switch to newer languages in order to encapsulate and name abstractions. We hide internal details and expose some interface so that we don't have to think about internal details and interactions when working on a new layer. Imagine building a house out of bricks. We don't think about the insides of the bricks while we're laying out the bricks. We have some certain expectations of the bricks, but we don't care about the exact material composition. We assume the bricks are composable, that we can stack them to build the structure of the walls. A major selling point of object orientation is that you can make all these kind of units in software, and that we can combine them to make programs that are easy to understand. The reasoning is that because we can understand the pieces, when we put the pieces together, we also get something that we can understand. In my experience, industry problem domain abstractions via objects often don't allow me to forget as much about the internal details as I would hope for. All it does is group methods to data that they typically operate on. It's more for organization, not hiding. Pure functions make good bricks. Hickey claims that objects don't make the best unit for that. Pure functions are. There's not much to worry about pure functions. Pure functions take one or more immutable values and return a new immutable value. Pure functions don't change the outside world. So take function which takes an x, and then this function returns x plus 5. This is pure. Function which takes a y and then reassigns y to y plus 5 is not. In pure functions, both the activity is local and there's no notion of time. Pure functions are easy to change since the contract is only a function signature. No one cares if the inside implementation changes, for example, like using a different sort method. While pure functions deserve its own talk, what's important here is how do we evaluate what makes something a good brick? The main thing is that we have this property of lack of worry or concern, and that's what actually gives us scalable composability. You could actually force this pure function style on object-oriented languages, but most people don't. So to recap, we increase our power by reducing what we have to think about. We reduce what we think about by using simpler constructs that compose. Functions make a good brick. Objects are familiar but not simple. Familiarity to something induces blindness to their problems. So objects plus methods fail to meet this without thinking about criteria that we want in order to reduce complexity. But many interesting programs or systems are not functions. Google is not a function as it returns different inputs over time. So instead, most programs are participants in the world. They are not idealized, timeless mathematical calculations. Instead, they can be analysis pipelines that scour over the world collecting data, that then does some type of transformation, that then pushes the data back, that then pushes the data to buckets, publishes dashboards, sends emails, or potentially pages on calls. These programs have observable behavior over time, as they get input over time. So fundamentally, we are building programs that are processes. To recap, the complexity of these programs come from both the time process aspect and that they are agents or participants in the world. The meta strategy behind object-oriented programming is to take our mental models of reality and apply them to our programs. In object orientation, the idea was to recognize that we have objects in the real world. These things, they act on the world, therefore we should have the same thing in our program. The whole buzz around encapsulation cannot be the main selling point, as that's accomplishable in other ways as well. Hickey claims that object orientation was an attempt to capture the aspects of process and agency, and that it is flawed. He constructs this critique mainly by drawing inspiration from Alfred North Whitehead's philosophical advancements. Essentially, his meta strategy is having better mental models from philosophy gives us better tools to then make better programming constructs. From my modeling background, there is this saying, all models are wrong, but some are useful. For our case, we want to see if this helps or hinders our objectives. Are some aspects too simplistic? Even though objects want to embody this association with behavior with data, Hickey claims that there is this detrimental mixing of concepts related to time, including behavior and state. So even though objects are about process, there is no notion of time. Pure functions also don't have this concept of time, but they don't pretend to have one either, as they only deal with inputs and outputs. So with objects, there's nothing you can explicitly talk about with regards to time because they were born of an age when your program ruled the entire computer. Here, the system presumes a single universal shared timeline. Concurrency makes this not true. Locking is an attempt to restore this single timeline. From the inspiration of Alfred North Whitehead, the key hint here is that there's no provision for perception or memory. So in recap, while functions make good bricks, interesting programs are not pure functions. Useful programs are participants in the world. Real programs are processes. So a good strategy here is to use better mental models from advancements in philosophy. Even though all models are wrong, some are more useful in different contexts. Objects are too simplistic with regards to time. They assume a single universal shared timeline. That's it for part 1. We close hinting that we should be using a better mental model. In part 2, we will describe this new mental model called the epical time model. We will talk about why this model is important and how we might implement them as programming constructs. Until next time, take care.